So this is continuation of our last lecture on current electricity, where we discussed the Wheatstone bridge. So one of the application of Wheatstone bridge we discuss is to measure the unknown resistance. So if we are given an unknown resistance and we need to find a value, we can actually place it in a bridge format and find it. And that application, one of the application is meter bridge. So you see, meter bridge arrangement looks like this. There is a wire which is 1 meter in length, and there are two resistances, you can see, R and S. So one of the resistances is known to us. So let's say this is a known resistance, and S will be a unknown resistance, unknown. So we need to find what is S, what is the value of S, using this setup, right? So setup looks like this. You can see this is a wire, let's say AB, of length 100 cm, and this is a meter scale which is measuring the length of a wire, and this is from this metallic strip. These all are metallic strips. So from this metallic strip you see a galvanometer is coming out, and the other end of galvanometer is connected to this needle like structure. This is called jockey. So this is called jockey. So you can see this is like a four arms of a bridge, R, S, and two ends of the wire separated by jockey. So if we move jockey to the left, right, and center, and we will reach a point where this bridge will be balanced. Balance as in there will be no current flowing across this galvanometer. And then we say that this bridge is balanced. And if it is balanced, we can apply the equation which we derived in the Wheatstone bridge, right? So let's say that balance point comes at O, and this O is at a distance L from A end, left end. And if it is at distance L from A, it will be at a distance 100 minus L from B, because the net length is 100 cm, correct? The net length is 100 centimeter, right? Now let's say that now I have four bridges, right? I have four. If I need to draw it circuit using a circuit, let me draw it using a circuit. So this looks like this, you see. This is R, this is S, and these are two wires. They will also have some resistance. Let's say if I draw it like this, and this is my galvanometer with a jockey, and this is connected across this cell and a switch. So what are these resistances? Let's say this resistance is ROA, and this is resistance is ROB, right? So what is the principle? What is the equation we know? We know that the product of the opposite resistors are equal. R into ROB equal to R into ROS into ROA. So talking about what is ROA and ROB, so this wire is a wire of uniform cross section, and throughout it is of same material, right? So if I need to write, let's say A be the cross section of this wire, small a be the cross section of this wire AB, right? So if I need to write using equations of resistivity, what is the resistance given in terms of it is rho L by A. So I say that R is proportional to L if A and rho are constant. So for OA, it will be rho into L by small a, and for OB, it will be rho into 100 minus L by small a. Correct? This is clear. So it is just proportional to the length. So if I put everything over here, and I write it like R into rho L by A, which is equal to S into rho into 100 minus L by A. So rho by A will cancel out each other, and I can say that S equal to R into L by 100 minus L. So this is the value, this is the unknown resistance which I needed to find out. R is what I know. L is what I am getting from varying the position of the jockey and reaching the balance point, and L is the measured from the left end, right? And using that, I can come at the equation and I can find the unknown resistance S using this meter bridge setup, right? So let's say if R is given as maybe 100 ohms, right? 100 ohms, and S is something which we need to find. And let's say the null point, this point is called null point. The O is the null point. So if distance of null point from A end is, let's say, maybe OA is nothing but, let's say 30 centimeter, anything. For example, I'm taking 30. And I need to find what is S. So these are only the given parameters to us. What are the given parameters? One is the known resistance which is R and the balanced point which is distance between A and O. O is the null point. So O is 30. OB will be what? OB will be 100 minus 30. I can easily find, which is 70. And I know the equation. Right? What is the equation I know? I know that S by R, maybe I'll write it as S by R, is equal to OB by OA. OB by OA. Is this I know? Correct? S by R equal to OB by OA. Now, if I put all these values, I'll be able to find, not S by R will be equal to OA by OB, not OB by OA. And if I place all these, again, I think this is a mistake, this will be OB by OA only. So if I place all these values, I'll be able to find what is S. So S by 100 equal to OB is 70 by 30. So S equal to what? 70 into 100 by 30. So it is 700 by 3, and you'll be able to find how many ohms it is. So only things which were given to us in the question is R and the balance point, right? Rest, the unknown resistance, we need to find using these expressions only, and this can be asked in multiple ways. Sometimes this unknown resistance can be converted into a different fashion if I place one more resistor, let's say parallel to this or in series with this. But finally you need to know this is the equation you need to know, and you need to approach that way, right? So next instrument which we will discuss is potentiometer. This is how potentiometer looks, and basically potentiometer, as the name suggests, it is a measuring device which is used to measure the potential differences or even resistances of sources, the unknown sources. Like if we need to measure the resistance or a terminal voltage of a cell, we can use this instrument to do that. And this instrument looks like this. We have a wire AB. Across this we have a cell connected. You can see this E2 is the cell, which is the unknown cell. E1 is something which is known value to us, which has a known voltage to us. So E2 is something which is unknown. And C is the sliding contact. So like a jockey in potentiometer, this C is also a sliding contact which can be slid between A and B to find the balanced point, right? Now, if you see, we have indicated I and I2. I is the current supplied by E1. I2 is the current which is flowing inside this cell, E2, right? Now, at one point in this circuit, if you see, there will be a condition where we will have this balanced point and I2 will be 0. So there will be times where there will be current inside this cell I2, which we have indicated as I2, but there will be a point, if you slide this contact C, there will be a point where I2 will be equal to 0. So let's understand what is the relation when I2 is 0. So normally if you see, if I need to write a KVL here for let's say for this loop, if I need to write KVL, so you see the I is current coming till here, my I2 is going down, so this will be I minus I2 here in this. And if I try to write a KVL, this looks like E2 minus I minus I2 into let's say the resistance is CB, between C and B. So E2 will be equal to I minus I2 into RCB. E2 will be equal to I minus I2 into RCB, correct? Now, see. So at balanced point what happens? I2 becomes 0. There will be no deflection in galvanometer. I2 will be 0. So E2 will be what? E2 will be I times RCB. I times RCB. Now you see one thing. Again, this RCB comes at, let's say, some L1 distance from this sliding contact. This distance is, let's say, L1, right? Now, can I write it like this? That resistance CB, if we maintain same area, cross section, resistivity, so will be equal to some constant. So this is rho into L1 by A. So some constant into L1. So if I write it like this E2 will be K times I into L1. K times I into L1. So for a same E1, I being constant, K being constant, what is varying is length. So if I replace this E2 and place other cell, what will change is the length of this balance point, the position where balance point will occur. Nothing else will change. So can I write it like this, that E is proportional to L? The EMF of this battery is proportional to the balance point from the C to B, right? So if we place two unknown cells, or not two unknown, so one known cell E1 and one unknown cell E2, one by one, and we measure those balance points L1 and L2, can I write it like this, that E1 by E2 will be equal to L1 by L2? And if E1 is known, L1, L2 are the balance points, so I can find the unknown EMF E2 will be, which will be equal to E1 into L2 by L1, right? So this is how you can measure the EMF of an unknown cell using potentiometer. Given condition is you have a known cell also and you have both the balance points, means you have the setup which will allow you to find this L1 and L2, and then you will be able to find E2, which is your unknown EMF, correct? This is one of the application of potentiometer, which is called as measurement of EMF, measurement of EMF of a unknown cell. So measurement of EMF of unknown cell. So there is one more application which we will be discussing now, which is measurement of internal resistance of the cell. Now we will see the another application of potentiometer, which is to measure the internal resistance. So to measure the internal resistance, the setup looks like this. So initially this resistor is not into picture. This external resistance R or resistor R is not into picture. So I can break it up, right? So condition is like this only, which we had in the last application. So I2 gets a balance point and I2 becomes 0. At balance point, I2 becomes 0, correct? And I can now write E2 as, let's say, E2 as what? Like we wrote before, K times L1 and then I also. K times L1 into I, correct? And now what happens is, I am connecting a external resistor R. Now the potential difference across this battery is changing, which is, let's say, V2, and the balance point is also changing. So after connecting R, let's say the potential becomes V2, and let's say the balance point also changes. Balance points, let's say, change from L1 to L2. Balance point will change from L1 to L2, correct? So now if we compare with respect to the older one, right? If we compare with respect to the older one, now can I write like the V2 is equal to what? V2 equal to K times L2 into I. K times L2 into I, correct? So this is the equation 1 for us, this is equation 2 for us. So E2 by V2 is L1 by L2. Now what is the relation between EMF and the terminal voltage? What is the ratio? So to demonstrate that, this is a separate diagram. You see this diagram. You see it's the same structure. This is E2, this is R and the R, right? So there is no current. I2 is still 0, but the balance point has changed, so there is no current. So only current will flow in this circuit only, this loop only. So I is nothing but E upon R by R. And if I calculate V is between these points A and B, which is I into R. And the ratio, the R and R relation is given by this. So from here, if I calculate the ratio, it becomes R by R and plus 1. So this one becomes like R by R plus 1 equal to L1 by L2. R will become L1 by L2 minus 1 into the known resistance R which we have. And this is how we are able to calculate the internal resistance of this cell, which is small r. So L1 is the balance point when this capital R was not into picture. L2 is the balance point when capital R came into picture. And capital R, since it is the known resistance, this is what we know. And using this expression, I can calculate the value of unknown internal resistance, which is small r, placed with this cell. So you can ignore this cell. This is a standard cell. We are not measuring here. We are measuring what for this cell only. Everything we have measured for this cell, even the EMF also, and even the internal resistance also. So for EMF, we needed two similar cells, which gave us two balance point. We took the ratio. Both ratios are equal. For internal resistance calculation, we needed a external resistor as well, and one setup is enough. Correct. So next very important topic to solve the complex electric circuits is symmetry. So some circuits which looks kind of very complex and very giant, but actually if you apply these concepts, if you see they are symmetrical from some plane or line, you will be able to simplify those kind of problems, right? So let's understand what is symmetry by a small problem instead of discussing it theoretically more, right? So let's see, you can see this is a combination of resistors, right? And let's say I need to find equivalent resistance for this combination. Now, for this combination, if I need to find equivalent resistance, let's analyze this circuit. So this is a cell which is supplying current I, right? Let's say this is point A, this is point B, this is point C, this is point D, and this is point O, correct? Now, at point A, this I will get three branches, this, and this, right? This is the first branch, second branch, and third branch. So there are three branches which the current will see. And if you see, the two branches are kind of symmetrical. AC and AD, the branch is symmetrical. So whatever currents enters this top path AC is the same which will go through AD, right? So let's say I1 goes through AC and I1 goes through AD also. What is the current in AO then? You can calculate using KCL. What is the current in AO? It will come I minus 2I1. So 2I1 which came across the top and bottom path, that is subtracted from the whole current I. So the current in AO is I minus 2I1, correct? Now one more thing. Now if I see from the destination end, right? If I see from the destination end, it is exactly as similar as the source end. So this is the same three resistor combination here also. So you can say the current which will exit from here is I1. This is also I1, and this is nothing but I minus 2I1. Correct? Now, if you are not able to follow this, just reverse this polarity of cell. So if I reverse this, it will supply I1 which is same for this two, and I minus 2I1, right? Since this is symmetrical, the format of source and destination, the distribution at source and destination is exactly the same. Now if I apply the KCL at C point, right? You see, I1 is coming to C and I1 is exiting from the top. So there is no current going in this resistor CO. Right? Even if you apply at D, you see I1 is coming, I1 is going. There is no role of this OD. Even you apply at O, you see I minus 2 I1 is coming and I minus 2 I1 is going. So you can eliminate these resistors. And how to identify these resistors? So if you take line CD and if you draw a mirror here along line CD, you see the circuit is symmetrical. And if the circuit is symmetrical along that line, whatever points are coming, whatever joints you are seeing, whatever nodes you are seeing, you can remove those nodes. You can remove those connections because there is no current going in this. There is no current going inside those nodes, so you can just pull off those nodes. And now you see the circuit is so simple. This is just three parallel resistor combination, and you'll be able to appreciate and find the answer, which is 2R by 3. Right? It looked a bit complex, but if you applied symmetry, this is very simple. Correct? So we have one more problem. And if you see this problem, this is not exactly a problem of symmetry, but very related. Because the approach which we took in reaching to the conclusion of symmetry, we will use here as well, and we'll understand how can we simplify this problem, right? So let's see, this is a complex network given to us, and we need to find the resistance between A and B, right? So let's say, if I1 is the current I which is entering at A, it is distributed at I1, I2 and I3 here. I1 here, I2 here and I3 here. So three different currents, right? I1, I2 and I3, right? Now, again, at destination, if you see, these are the same resistors, 10, 5 and 5, and even these 2.5 are symmetrical here. So in destination also, the exit currents will be the same as incoming, and you can understand this by reversing the polarity of cell, which you will place if you want. And if I1 is entering this 10 ohm, the exit current from 10 ohm will be again I1. The exit from 5 ohm will be what? This 5 ohm will be I3, and here it will be I2. Correct? So you see the distribution has changed, but it is across the same parallel distribution. The current which is entering 10 ohm is the same which is living through the 10 ohm. If you see the symmetry nature at source and destination, might be you are not able to find a line of symmetry here, but the nature of symmetry is such that the same three combination is coming at the destination also, and you are able to apply the distribution of currents in that way. Now you see one thing. Let's say this is the point O. So whatever current is entering in this AO is same as what is entering into the BO. Whatever current is entering to the AO is same what is entering the BO. Correct? Now if I apply this KCL at O, so whatever current is in this branch will be the same which is in this branch as well. Let me name them as maybe C and D. So whatever current is in CO will be the same which is through DO, because since these two are same resistors also, so distribution will be same. Now so these two lines are now kind of independent to each other. They might look to be crossing, but if you see by symmetry, this 5 ohm and 5 ohm is like in series, same current is going, and this 2.5 and 2.5 are in series because same current is going, and I can redraw this circuit by bringing this 10 ohm together and bringing this 5 ohm together, right? So between AB I bring this 10 ohm, and between CD I bring this 5 ohm, because they are now independent because same current is flowing. So if I redraw this circuit, I can redraw it like this. So this is 10 ohm, this is 5 ohm, this is 5 ohm, this is again 10 ohm. So this is nothing but 10 ohm, 10 ohm, 5 ohm, 5 ohm. This is 2.5 plus 2.5, which is now 5 ohm. This is point A and B, and I need 10 ohm again in between A and B, so I'll just take a parallel branch here, which is 10 ohm, and these are my points. This was C and D. O has been removed from the picture. Now you see, now we'll be able to find the equivalent resistance of this combination easily, right? There are multiple ways to find the equivalent resistance now, but the circuit looked a bit complex here, but we simplified it to this one, and now we'll be able to solve this very easily. So we'll solve more problems like this as we move ahead in the next lectures, and we'll see more different complex problems and some relevant topics which are pending for this chapter before we move to the next. Till then, thanks.